Finxters. This is the second video on the math module from the Python standard library. We're going to talk about 5 functions from discrete mathematics: factorial, permutation, combination, the GCD, and LCM. The first 3 are combinatorial functions. Combinatorics is the mathematical study of counting finite objects, which for our purposes means counting the number of ways of choosing or rearranging different objects. And the latter two, GCD and LCM, are number theoretic functions. And number theory is the study of integers and rational numbers. And elementary number theory especially concerns largely with divisibility of integers. We'll get back to this later. With the factorial function. So to understand a factorial function, let's look at an easy example and understand it well so that we can generalize it to harder examples. So let's count the number of ways of rearranging the letters A, B, and C. Well, since there are only 3 of them, we can write out all the possibilities. We have ABC, ACB, BAC, BCA, CAB, CBA. And so there are 6 possibilities. But since we want to have a more systematic way of approaching this, let's group together these rearrangements into groups. So the first group are the rearrangements with the first letter A. So you have A, B, C, A, C, B. And the second group are the ones that start with B. So B, A, C, B, C, A. And the third one is the ones that start with C. And the point I want to make here is that you can think of this as a tree. So the first, so you can think of the A as a branch, like so, and the B's as another branch, and the C's as another branch. So there's first 3 branches. And from each branch, there are two other branches coming out. So there's the AB branch, the AC branch. And then finally, there are the nodes like so. Likewise, there are 2 branches coming out of the B branch, and then there are 2 branches coming out of the C branch as well. So how can we count all the nodes on this tree? Well, there are 3 branches first, and then there's 2 branches, and then there's 1 branch. And then there are the rearrangements. So it's 3 times 2 times 1, which gives you 6. We can see that we can abstract this approach to 4 letters. So here I've written up the A branch. So you can first have the rearrangements starting with A, and then you have 3 other possibilities coming from this branch. You have A, B something, something, AC something, something, AD something, something. And respectively, so there are 3 branches like so, and then there's 2 branches coming out from each one of them, like so. And you also have branches with B in the first slot, and then you also have the one with C like this, and D like this. And from each one of these, there are 3 branches from which there are 2 more branches coming out. So if we wanted to count the rearrangements here, once again, you just have to multiply 4 times 3 times 2 times 1, and you get 24. So the main point here is that expressions like this, where you multiply 1 through some number, some integer n, in this case 3 and in this case 4, expressions like this are very useful in discrete math. And so we give them a special notation. So we write an exclamation mark next to the number we want to multiply up to, and we call it 3 factorial and 4 factorial respectively. So this is what the factorial function does. And since this is a Python tutorial, we're going to see how this can be implemented in Python, and that is very simple. So you first call in the math module, and then you just write math.factorial, and you can do math.factorial 4, and you get 24. And likewise, you get, so yeah, factorial 3 is 6. And using this, actually, we can calculate the number of ways of rearranging the entire alphabet. And since there are 26 letters, there are this many. And I think this is enough to convince you that you certainly cannot write out all the possible ways of rearranging the alphabet. Or, well, you can, but it's going to take you a very long time. And I would just like to mention that the factorial function grows very quickly, and it grows much quicker than the exponential function. And this the growth of the factorial function is not entirely obvious. It's not really clear how to. If you just look at the definition of the factorial function, it's not clear whether it grows faster or slower than the function like 2 to the n or something. And to answer this question, there's the formula called Stirling's formula, which is this formula down here. Stirling's formula, where the squiggle is called the asymptotic notation, which means if you take the ratio of this, and if you take n to infinity, the ratio goes to 1, where limit is in the sense of calculus. If you want more details on this, please look at my math.factorial article on the Finxter blog. I would only like to just point out that these things exist and that they're very cool. The idea here is that I'm just going to describe this very briefly, that the factorial function can be described by what's called the gamma function, which is defined by this integral formula, which looks all complicated and scary, but all it is the area under this graph. This big one is the case when n is equal to 4, and this one is 1, 2, 3, 4. And as you can see here, as n gets larger, you get larger bump functions. And I'm just going to describe this briefly, but the idea for proving this formula is to have a nice approximation for the area under this graph. And at least one way of proving this is to see a similarity between this function and the beloved normal distribution function, or the Gaussian function from statistics. You can see by comparing these graphs that the integrand in the Gaussian looks very similar to, or the integrand in the gamma function is very similar to the Gaussian function. And you can use techniques for evaluating the area under the Gaussian to get a reasonable approximation to the gamma function. And that is roughly how you get this asymptotic formula, or this approximation formula for the factorial. That's all very technical, and you don't really need this to understand the Python math factorial function, but I think it's very important to understand how fast these things grow and things like that when you actually have to work with the factorial function. Let's now move on to the permutation function. So as we did for the factorial function, let's look at an example. So what are the number of ways of choosing 3 letters from the letters A, B, C, D, E with different rearrangements? So what do we mean by this? Well, we want to count things like A, B, C, because those are 3 letters, shows up from here. We want things like B, C, D, and also we want things like BAC. BAC is different from ABC because we're considering different rearrangements. You cannot do things like AAB because you cannot choose the same letter twice. Okay, and you can see that this problem is distinctly similar to the problem we've seen before, and indeed it is. So, a problem we've seen before in the factorial section. So how can we think about this? Well, we can use the same idea we did before and write down the rearrangements in a tree. So we can first write down the rearrangements with A at front. And what are ways of doing that? Well, the next letter can always be B. It can be C. It can be D, and it can be E. And after B, you can have C, D, or E, right? So you can have A, B, C, A, B, D, A, B, E. And likewise, there are 3 branches here, right? And you can have 3 branches here, and there are 3 branches here. And other than having A up front, you can also have B, C, D, and E as the first letter. So if we take this into account, we can use the same idea as before, right? So there are first 5 branches, A, B, C, D, E. So it's 5 times, next you have 4 branches. So you have the AB branch, AC branch, AD branch, AE branch. Under the B branch, you can have BA, BC, BD, and BE branch, right? Again, there's 4 branches. And then there are 4 branches coming out of the C branch, the D branch, and E branch, respectively. So you do 5 times 4. And then from each of them, so in the AB branch, there are ABC, ABD, and ABE. So times 3. And then you have and then since we're only choosing 3 letters, we're done, right? So we have ABC, ABD, ABE. So to count all the different rearrangements, we just have to calculate this, which is what? It's just 60. Okay. So this is the permutation of 3 letters chosen from 5 letters. And there's a mathematical shorthand for this. In textbooks, it's often written as 5p3. So the 5 is the number of letters, and 3 is the number of letters you're going to choose from the 5 letters. So this is read 5 permutation 3. And again, how do we implement this in Python? Well, it is you just have you have to import the math module, and you have to use math.perm, and you get 60. And the default value for the permutation function, the default value for the second parameter is none. So if we do this, if we do perm of 5, we get back 120, which is the same thing as it just gives back the factorial. So if you leave the second parameter blank, it just gives back the factorial. We're going to look at the combination function. To understand a combination function, once again, we look at an example. So what are the number of ways to choose 3 letters from the collection A through E, not counting rearrangements? By this we mean ABC is counted as the same thing as ACB because they're the same letters rearranged. Likewise, there are 4 other possibilities like so. But of course, ABC is counted differently as ABE because they're literally choosing different letters. And so when you see this problem, you first notice that it's very similar to the problem we had with permutations, where we did count for rearrangements. So in other words, ABC was different from ACB in the permutation problem. And how do we... And for the permutation problem, we just do 5 permutation 3, which is 5 times 4 times 3, and there's 60 possibilities. So in other words, there are 60 ways of choosing 3 letters from A through E, counting rearrangements. So hopefully we can modify this in a nice way to get the solution to our current problem. So the main idea here is that one way of choosing the letters accounts for 6 ways of choosing the letters in the permutation problem. So if we had ABE as well, there are 6 ways of rearranging it. So you have AEB, BAE, etc. So there are 6 ways. 6 ways. There are 6. So given a way of choosing the letters in the combination problem, there are 6 ways of choosing them in the permutation problem. What does this mean then? Well, the solution to our problem then should be, so it should be 60 divided by 6, because each of the possibilities in the combination problem, which is the problem with not counting rearrangements, corresponds to 6 possibilities in the permutation problem that we've seen before. So 6 out of these 60 should correspond to 1 possibility here. So it's 60 divided by 6, which gives you 10. And since problems like this of counting the number of ways of choosing things, discounting rearrangement, comes up a lot, we have a special way of writing it in mathematics. It's written 5C3, or it's also written 5 choose 3, like so. And the reason why this is also called a binomial coefficient is because they are the coefficients to expressions of the form 1 plus x to the n. So for instance, if you had 1 plus x squared, you might recall from middle school algebra that you can expand this out and get 1 plus 2x plus x squared. And so the coefficient is 1, 2, and 1. And indeed, this is 2 choose 0, 2 choose 1, and 2 choose 2, etc. There are a lot of textbooks that talk about this, so we'll not go into detail here. Let's look at how to implement this in Python. So as always, let's first import the math module. And we use math.com. And that's the syntax. To find 5C3, it's just math.com 5, 3. If you run it, you get back 10. We can try out a few more examples. So if you wanted to find the second coefficient of 1 plus x squared, then you get the coefficient of x to the 1 in 1 plus x squared is math.comp of 2 comma 1, which is 2. An exercise is for you is let's find the coefficients of 1 plus x to the, how about this, 1 plus x to the 10. Find the, let's see, the coefficient of x to the 4th of 1 plus x to the 10. So what's the coefficient of that? Well, you can find that using Python. So it's 10 comma 4. So it's 2 to the 10. So what do I mean by this? You're gonna, if you expand this out, you're gonna have a lot of junk plus more junk, and then you're gonna have a term that looks like x to the 4, like this. And then the other terms are like some coefficient. Can choose 3 here. Here, and then 10 choose 5 over here. So if you expand this expression out, you're going to get something like this. And we know this 210 because we just calculated over here. So that is the combination function. Our first function is the Gcd function, or the greatest common divisor function. So what is the Gcd? Well, as its name implies, it is the greatest number that divides the 2 or more given integers. So as an example, let's look at the GCD of 12 and 16. Well, the divisors of 12 are 1, 2, 3, 4, 6, and 12. The divisors of 16 are 1, 2, 4, 8, and 16. Therefore, their common divisors are 1, 2, and 4. And so the biggest of these is 4, so the GCD is 4. Let's look at another example. So what is the GCD of 15, 18, and 21? Well, the divisors of 15 are 1, 3, 5, and 15. For 18, it's 1, 2, 3, 6, 9, 18. For 21, it's 1, 3, 7, 21. And so if you compare the 3 lists, you see that their common divisor is only 1 and 3. And therefore, the largest of this is 3, so the GCD is 3. So this is all nice, but this method relies on you writing down all the divisors of the given numbers each time you have to compute a GCD. And this is a very difficult task if you have to compute the GCD of 2 large numbers. So we want a better method of doing this. The standard way of doing this is to use the Euclidean algorithm. And since this is a Python tutorial, let's look at a Python implementation of the Euclidean algorithm. So what is the main idea here? So let's calculate the GCD of 25 and 11. Let's look at this problem. So the idea is you take the larger of the two, which is 25, and divide it by the smaller one, so 11. So 25 divided by 11 is equal to 3, and the quotient is 2, or 2, and the remainder is 3. Next, what you do is you take 11, and you divide it by the remainder you just got, which is 3. So 11 divided by 3 is 3, remainder 2. And then you just repeat the same process. So you take 3 again, and you divide it by 2, which and the remainder is 1. And the amazing thing is that this last remainder is actually the GCD. And we will not prove this. We will not prove why the Euclidean algorithm works in this tutorial, but there are plenty of textbooks that talk about this. If you pick up any textbook on elementary number theory, it usually discusses why the Euclidean algorithm works. And what we just described here is what we've written in this code. It's a very good exercise to go over this code and see why it works. And as expected, if you try running this code, so the GCD of 12 and 18 gives you 6. If you do 25 and 11, as we just did, it gets back 1. If we try another pair of numbers, like say 108 and 201, it gives you 3, etc. And notice here that the Euclidean algorithm, as we've written it here, only takes in 2 inputs, n1 and n2. So we can't directly calculate GCDs like this using the Euclidean algorithm, but there is a workaround. So what is the workaround? Well, the idea is if you want to calculate a GCD of 3 numbers, like so, the idea is to take the GCD of the first 2. So calculate the GCD of the first 2, 15 and 18, and then take the GCD of that with the third number, like so. So what do we mean? What do we mean by this in terms of the algorithm? Well, if we wanted to calculate the GCD of 15, 18, 21, this just means that we have to calculate the GCD of 15, 18, and 21, like this. And then it does indeed give you 3, which is what we got earlier. So what is the least common multiple? Well, as its name suggests, it is the smallest number that is divisible by the 2 or more given numbers. Let's look at an example. So what is the LCM of 12 and 18? Well, if we write out all the multiples, or the first few multiples of 12 and 18, you get 12, 24, 36, 48, 60. And for 18, it's 18, 36, 54, 72, etc. And you can see from this that 36 is the smallest multiple that appears in both lists. So the LCM of 12 and 18 is 36. How about 4, 6, and 10? What's their LCM? We can take the same approaches here, except let's start by writing out the multiples of 10, which is the largest of the 3. So you have 10, 20, 30, 40, 50, 60, 70, 80, etc., etc. And we just observe here that the LCM of 4, 6, and 10, their LCM must appear in the list of multiples of 10. So actually, we could write out the multiples of 4 and 6 as we did in the previous example, or we could look for the LCM in the list of multiples of 10. So which number of these is divisible by 4 and 6? Well, if we look at these, we notice that 60 is divisible by both 4 and 6, but 50, 40, 30, 20, and 10 are not. Therefore, we can conclude from this that the LCM is just 60. But as with the GCD, if we have to write out the multiples of the numbers every time we calculate the LCM, it's a little hard. It's a lot of work. So we want an easier way of calculating the LCM. Well, fortunately, you have this lovely relation that the product of two numbers is equal to the product of their LCM and their GCD. So we can confirm this. So for this example, we can use either the Euclidean algorithm or the writing out the divisors of 12 and 8, that the GCD of 12 and 8 are just is just 6. And therefore, if we take the product of the two, we can confirm that their product is just, well, what is it? It's 216 times GCD equals 216. And we can confirm that 12 times 18 is also 216. We can do the same calculation, and this relation holds in general for only a pair of numbers, and we can use this relation to calculate LCMs because we know how to calculate GCDs, and we certainly know how to calculate the product of two numbers. So using this relation, we can calculate LCMs for a pair of numbers. In order to calculate the LCM of 3 or more numbers, we actually have a relation as we did for GCDs. So if we had A, B, if we wanted to calculate the LCM of A, B, and C, we can just calculate the LCM of the first two and calculate the third. So in order to calculate the LCM 4, 6, and 10, it's sufficient to calculate the LCM 4 and 6, which is just 12, and then calculate the LCM of 12 and 10, which ends up being 60. So how do we implement all of this in Python? Well, as we did before, we can first import the math module, and then use the math.lcm function. So if we wanted to find the LCM of 12 and 18, we can get back 36. And if we have LCM of 4, 6, and 10, we get back 60 as expected.